dB per bit in a PAM system. Extra 6 dB to send one more bit through the system. Now this is kind of logarithmic in some sense. So if I'm fixing the symbol rate and I want to get a very high data rate, what happens is every time I increase the power by 6 dB, that's another factor of 4. So I really need a lot of power, or I really need a very small noise in order to get a lot of bits through the channel. But as long as those conditions are met, here's a table, then we can go ahead and do that. Now this is for 10 to the minus 6. You could do the same thing for 10 to the minus 9th, and what you would see is that you need to add 2 dB to all SNRs to get that. That's a lower probability of error. For 10 to the minus 7th, it's add 0.7 dB. And if you only wanted 10 to the minus 3, you can actually subtract 3.5 dB from all signal-to-noise ratios to get that. So it just depends on what is your target. Okay, now sometimes high probability of error, which is low performance, is acceptable. Okay, transmission system may be doing something at a higher level to fix errors. It may be voice traffic. Voice is not very sensitive if it's digitized voice to errors. You can make a few errors, it doesn't make any difference. The person on the other side can still figure out what was being said. Okay? If it's a transmission system that's sending emails, okay, you might want to have a very low probability of error. Now, granted, TCP/IP, if you know anything about that, if the packet doesn't get through, there's a little check and it asks for retransmission. So you're basically guaranteed 0 errors, or the system won't deliver your email. It'll send something back to the transmitter saying it didn't get through. So it checks itself. But you might not want to have to retransmit packets that often in the email system, so you might want a very low probability of error on the transmission path. So sometimes the choice of operating point depends on the types of signals that are being sent through the transmission channel itself. Okay, so that's PAM. Pretty easy. Okay, one-dimensional transmission system, very heavily used. You know how to design the transmit constellation. You have a basic idea of what the receiver is about, and even more importantly, if you were to measure the signal-to-noise ratio for the channel, you would be able to work backwards to about how many bits per second you could transmit through the channel. Now you'll start to see in homework next week on problem set number 3, you'll see some problems. You'll see in the back of the book that I have a lot of former exam problems that show up, and I usually mark them, so that gives you an idea when you're studying for midterm or final exam. Oh, okay, this is how Cioffi thought the last 10 years, so you can see I'll have new problems on the exams, but it's kind of hard for me to think outside the box after teaching the class as many times as I had, so that'll give you a good indicator for the exams. But also you'll see some problems that begin to ask you things like, go ahead and figure out the signal-to-noise ratio. How many bits per second could you get through this channel? What's the PAM constellation that you would use to transmit over this channel? And that kind of gives you a high-level engineering viewpoint of how to quickly analyze these channels. You memorize maybe one signal-to-noise ratio and you just offset with respect. You get a pretty good idea how fast you can transmit on this channel without going through a lot of analysis to get there. If you want to get the details, the exact probability of error, then you have to work it out. But you'd have a good idea of about how to design a system, how many bits per second you could get through that system. Now, QAM is even more heavily used than PAM. And this is typically for bandpass channels. So channels that don't pass DC, we often see QAM being used. Now, the number of dimensions in QAM is not 1 anymore, it's 2. And the 2 basis functions are typically pick your favorite PAM basis function, multiply it by square root of 2, and then also multiply it by cosine of some frequency. We'll talk a little bit more about the frequency momentarily. and sine of that frequency. Sometime you'll see in the notes I'll put a minus sign out in front of the second basis function. It really doesn't change anything. It just makes some of the mathematics look a little more convenient later on. Some of the formulas we're going to use will simplify a little more nicely if I have a minus sign. Now what's going to happen with these two functions? We know when we multiply by cosine anything, basically what happens is we get this, the Fourier transform. We take the sum of the frequency with the cosine and slide it, basically the original Fourier transform, up to that frequency, and we slide it down to the negative frequency, right? So we're taking kind of a low pass and moving it up to some frequency. And we're doing that again with the sine function, but it turns out if we multiply this one by cosine and that one by sine, if this is already a normalized basis function, these two are also normalized and they're orthogonal to one another because the sine and the cosine are basically orthogonal. So what I'm getting is a bandpass type modulation system, and it's going to be centered at the carrier frequency. Now obviously I need to pick a carrier frequency that's at least twice the highest frequency of phi of t, or I get kind of a ridiculous system. It's not going to look bandpass. So the carrier frequency basically has got to be a lot higher than the signals of interest. In wireless, this would not be a problem. Typically we see carrier frequencies in wireless that are often hundreds to thousands to millions of times the actual bandwidths of the signals, and they're being narrowly stitched in some band that the FCC allows to be used for transmission. Wireless LANs, for instance, if you got one on your computer, 802.11, is either going to be around 2.5 gigahertz or around 5 gigahertz for this carrier frequency. The actual bandwidth of the signals being sent are only 20 megahertz in those systems. So that's a lot less than 2.5 or 5 gigahertz. They look tiny on any kind of reasonable plot of scale with respect to that. So that's a lot different than a PAM system where it's basically down at DC. Now, the two dimensions allow us to plot nice constellations on a piece of paper. And I often wonder if this is the reason why QAM is so popular, because we can easily draw it. One dimension, we really don't use all of the paper. We just had a straight line. But two dimensions, we can nicely handle that. And the most heavily used constellations are the QAM square constellations. And m in this case is going to be 2 to the b again, which now, because it's a two-dimensional constellation, is going to be 2 to the 2b bar. Okay, because b bar is b divided by 2. So to get b back here, I got to have a 2 out in front. And b, which is 2 b bar, is even. B bar is an integer. Now I'm going to handle odd numbers momentarily, so we haven't forgotten them. But for the moment, we're just going to deal with even number of bits per dimension. Sorry, integer numbers of bits per dimension and even numbers of bits per symbol. The first QAM square constellation, therefore, has 4 points in it, because if b bar is 1, first integer, I get 2 times b bar is 2, so I have 4 messages or 4 points in the constellation. And if I were to draw the axes in, it would look something like that. So I have 1 point in each quadrant, and the points transmitted are going to, if I were to look at the crossing points here, it's going to be d over 2, minus d over 2 over here. And the same thing on the vertical axis. A little hard to write it because I'm leaving space. I'm going to draw some more points here. So my pen is too fat. But this is d over 2 here, d over 2. And again, this is in your notes. There's a nice big QAM constellation drawn in your notes, so you could look there. Now clearly the distance between points is again d. So probability of error is going to be determined by the product, again, of the nearest neighbors and q of d over 2 sigma for such a transmission system. If I instead go to b bar equal 2, 2 times 2 is 4. That gives me 4 bits or 16 levels for transmission, So give me another QAM square constellation where again all the closest points or nearest neighbors are spaced at distance d. So the vertical axis crossing point here would be 3d over 2, 1d over 2, and same thing in the other dimensions. So we go from -3 to +3 in each of the two dimensions, -3, -1, 1, and 3, all times d over 2, and I get 16 points in the constellation. If we were to look up here in the corner at these points, the corner points would be square root of m over 2 minus 1, square root of m over 2 minus 1 times d. And then again, you can play with this. You can see, well, of course, if m is just 4, then square root of 4 is 2 over 2, which is, sorry, do I have this right? Yeah, minus 1. I have 2 over 2 minus, it should be a 3 here. Hang on, I have square root of m is yeah, if m is 16, right, okay, square root of m is 4 over 2, which is 2 minus 1, which is, square root of m is 16, I get 4 over 2, I've done something wrong here. Oh, I have d over 2. Pull this outside, that's what I've done wrong. Okay, so then I get 3d over 2, 3d over 2. Somehow that mistake made it through on my notes. So again, the corner points here, kind of like the points that we saw for the PAM constellation, except what's happening is where you saw an m earlier, now we get square root of m. Okay, and that's because we're doing this in 2 dimensions instead of 1 dimension. Yes, sir. Microphone, please.
Why did you consider that large?
So I'd get square constellations. That's not a square QAM. It's another type of QAM that I'll get to. So the squares are a little easier. Once you get the idea of this, then we'll go back and get the odd numbers momentarily. So again, I could continue this type of construction. I could have the next size square would have actually 8 by 8 or 64 points in it. After that, I would have 16 by 16 or 256 and so on. What's the largest size QAM squares? Believe it or not, you can see up to largest QAM squares I've seen have 16,000 points in them. So and that's possible to do that, again, if you have enough signal-to-noise ratio in the transmission system to be able to do that. If I were to work the relationship between the energy per symbol and the distance between the points, which is fixed at d, in the square constellation, it works out to be d squared over 6 times m minus 1. Now this is basically just algebra to do this, and I have it detailed in the notes, and there's no point in going through it here in the class. Ex bar would be 1/2 that because we have 2 dimensions, so it's d squared over 12 times m minus 1. This is almost exactly the same formula as the PAM constellation, except I have square root of m where I had m previously. And that makes a lot of sense. Basically, all we've done is taken a PAM constellation and followed it by another PAM constellation and looked at it in 2 dimensions. We'd get a square also. So we should be seeing basically the same formulas occur for QAM. The basis functions may be different than 2 successive PAM transmissions, but the constellation itself is going to be the same. If I were to then work the relationship d over 2 sigma, it's a little easier to do it squared. It works out to be 3, not over m squared minus 1, but over m minus 1 times the signal to noise ratio. The number of nearest neighbors is a little bit harder to get. We can see that interior points in the middle have 4 nearest neighbors. And then there's 2 types of outer points in this constellation. Some of them, like here in the middle of this outside branch of the square, we'd have 3 nearest neighbors, 1, 2, and 3. But this point over here only has 2 nearest neighbors. Okay, so we have to take that. We're going to have 4 points with 2 nearest neighbors, and then we're always going to have some number of points with 3 nearest neighbors, and then everything else in the middle is going to have 4 nearest neighbors. We go through and we actually count that. We will get 4 times 1 minus 1 over square root of m as the average number of nearest neighbors for a square QAM constellation. And in this case, it's not an exact equality. It's an upper bound, but it's a very tight one. The probability of error is 4 times 1 over square root of m times q of 3 over m minus 1 times the signal to noise ratio. Now somebody asked, yes sir?
Why is it a bound instead of an exact approximation?
Basically, the points here on the outside of the system, if you had a very, very large noise, because they have an unequal number of nearest neighbors out here, it's possible we're doing a small amount of double counting, okay, in essentially the probabilities that could occur. So it's not quite the same as the PAM system because we're in 2 dimensions. So if you play around with this corner point, you'll see there are ways for very large noises, which are very unlikely to occur, to cause this to not be an exact bound. The only time it's exact actually is when m is equal to 2. Sorry, when m is equal to 4 or square root of m is equal to 2. So this is the probability of error expression for QAM. Very tight expression. So we could, of course, again, look at a receiver. What would happen is I'd have to have 2 match filters, one matched to this, another one matched to that, sampling them both at the symbol rate, getting 2-dimensional outputs, and what I would do is look at the closest point in this square constellation, which I could probably do with a couple of truncations. If I added the little minus d over 2 again, truncated the real dimension, truncated the horizontal dimension, truncated the vertical dimension, I could pretty much decide the closest point in a square constellation. And I would have a nice detection system. And the basis functions are kind of set up for transmission through some kind of bandpass channel. Now we're going to spend a lot of time on the basis functions in Chapter 2, which will start a little bit on Thursday and then into the following week when we start looking at what are called bandpass analysis of systems. So and then we'll see exactly how to implement the receiver. There's some simplifications that we can make with respect to just having the 2 basis functions in parallel. We won't talk about that quite yet this week. We'll just look at the design of the actual data symbol values themselves. And the QAM square is easy. Now, just to note here, somebody asked me about the signal-to-noise ratio formula. Is it always square root of SNR? Well, guess what? If I put in 4 points in the constellation, the 4-point QAM square, which is sometimes called QPSK, quadrature phase shift keying, m is 4. 3 over 4 minus 1 is 3 over 3, which is 1. So I get square root of signal-to-noise ratio again. If m is 16, the next number up, to go from 1 bit per dimension to 2 bits per dimension, or equivalently go from 2 bits per symbol to 4 bits per symbol, I get 16 minus 1, or 3 over 15, is 1/5. There's the 5 again, losing 7 dB, where it takes me 7 dB to send an additional 2 bits per symbol. Well, that's the same as sending an additional 1 bit per dimension. In PAM, we saw 1 bit per dimension was costing 7 dB to be able to send it. And we could continue. We could create a table if we wanted. For QAM, it would look a lot like the table for PAM. And in fact, I have one of those in the notes, and you can make that comparison if you like. Somebody asked about odd B. And unfortunately, we have to break it down for several different situations with odd B. Now, the first one someone just asked about, if B is equal to 1, I'm going to call this a QAM cross. The first couple of constellations are not really going to follow the rules of that for B equal to odd. But the best place to put the 2 points. You could put them up here in the corners if you want, or you could put them on one of the axes, in which case you'd really have a one-dimensional system where you're wasting the other dimension. And we could go ahead and compute the distance between the 2 points and just have Q of D over 2 sigma. For this system, obviously, these are both on a circle where the radius squared is the energy, so you could work backwards and get the D from that case. This is sometimes called binary phase shift keying, BPSK. For B equal to 3, it's ugly. This is well known in transmission. There's like no way to get 8 points in 2 dimensions that's tremendously energy efficient. So you see weird stuff that looks like this, so-called spoke constellation, because it looks like it's got spokes